After dealing with VLANs, which are layer 2 technology, and inter-VLAN routing, which is layer 3, let's step down a little bit and talk about layer 2 topology. And in particular, what I'm interested in this video is to see what happens if there are multiple connections between switches. So my topology looks like this. If I do show CDP neighbor command, and basically I can recreate a topology in a topology diagram. What I see here in this topology, that there are multiple connections. So for example, switch 1 has connection towards switch 3, actually two connections. One is over port E4./2, the other is E4/3. In a similar way, it has connection to switch 2 over port E4.0 and E4.1, and all switches have redundant connections for resiliency purposes. But at the layer 2, that is going to create a few problems. Okay, let's consider what happens, let's say, when PC1 is sending ARP request trying to find out the address of PC2, for example. It sends the ARP request. The switch 3 learns the source MAC address of PC1 by reading its source MAC from the Ethernet frame and maps this to the port E12. But then looks at the destination MAC address and its broadcast, all Fs. So it sends this out of all the ports, and assume, let's say, that all ports belong to VLAN 1. So it sends the traffic out port E4/2 towards switch 1. Let's say that this one came in first. So now switch 1 reads the source MAC address of PC1 and maps its source MAC address to this port E4/2. Maybe a fraction of a second later, the same broadcast is sent over E4/3, and now switch 1 realizes, oh, source MAC address changed its position from E4/2, and now it's sent across, and it can be learned on E4/3. So remaps that, obviously. So that's going to create a problem already in MAC table instability. What happens later? This is a broadcast, so it sends the port out, the frame out of port E4/0, and the same thing. Switch 2 reads the source MAC address, it learns the PC location PC1 source MAC address is on that port, but then maybe fraction of a second later it comes on E4/1. Oh, it changed its location. So let's just put this now, map the source of PC1 to 4/1, sends the broadcast, and all of a sudden the broadcast comes down here over E50 on switch 3, and switch 3 realizes, oh, PC1 was remapped and it's changed its location. Now it's available over E50, which is not true because it's still connected to E12. But because the broadcast was sent here and switch 3 learns the source MAC address of a sender on that port, it maps the source MAC address of PC1 to that port, and as of this moment is completely inaccessible, and the traffic is actually looped. So if switch 3 was supposed to send this broadcast again, sends this down here, up here, up here, and we form just a loop. Now that loop is going to, sooner or later, probably sooner than later, is going to bring the whole system down, because the CPUs are going to be nuts, crazy, sending this broadcast in around this loop, around this loop, and around this loop, and around this loop. All the loops will be forwarded that broadcast. That obviously cannot work like that. This is why the designers came up with a solution to this multi-path between the switches, and that solution is called spanning tree protocol. There are 3 flavors you can use on Cisco switches, but they all share the same basic operation. So in the next video, I'm going to talk about terminology. We take a closer look at the command line interface and how it operates based on the principles, and we'll see how the system selects one single path between all the switches so that the loop does not form. Should one of those interfaces fail, another will be chosen to create again loop-free topology at the layer 2 on those switches.